We have been studying bivariate relationships. We're now ready to move to the third and final variable combination, two categorical variables. Let's begin by looking at the steps that we are going to take to analyze the relationship among two categorical variables. First, we will graphically illustrate the relationship with stacked or grouped bar plots. Next, we will calculate either conditional proportions or conditional percentages and display these in a contingency table. Finally, we will compare the conditional proportions or percentages for each category of one variable across the categories of the second variable. Now we're going to need to learn how to take each of these steps. But even though the specific methods might seem like gibberish to you until we learn how to accomplish these tasks, the sequence should look familiar. We graphically illustrate relationship, we calculate statistics that provide more specific information than the graph, and then we study those statistics to determine if there is a relationship, and if so, the size of that relationship. Yes, we need to learn the specific steps, but from a meta view, you already know the routine and why we go through that routine. Here are bar graphs for two categorical variables for data that were collected from the Titanic disaster. The first bar graph illustrates the composition of passenger class. The second variable illustrates the survival rate. The study of these two variables is informative in and of itself, but there is a more interesting question we can explore. Is passenger class related to the survival rate? These are two categorical variables, and that is a relationship question. So this will provide our first example of analyzing the relationship among two categorical variables. Here is what we call a stacked bar plot. Each bar represents a passenger class. The total number of passengers in each class is included in each bar because each bar has a total proportion of 1, which is 100% of the passengers in that class. Carefully note that I am talking about 100% of the passengers in that class and not all the passengers on the Titanic. Each bar represents a different passenger cabin class, and all the passengers in that cabin class are represented in that bar. Now let's focus on the colors. The legend in the lower right corner tells us that the red represents perished and green represents survived. I can see in the first bar that about 0.4 or 40% of the passengers perished. About 60% survived. We are talking about 40% and 60% of the passengers in first-class cabins. When we look at passengers in second-class cabins, we see that the survival rate decreases. When we look at passengers in the third-class cabins, the survival rate decreases even more. This difference in the survival rate for the different cabin classes indicates that the survival rate is related to the passenger class. These two categorical variables are related. Another way that we can illustrate this relationship is with a grouped bar plot. This bar plot provides the same information, but in a different format. Rather than the colors being stacked on top of one another, they are placed side by side. You do not need to illustrate relationship with both types of bar plots. In fact, you should not. That would be redundant. Which one you use is a matter of personal preference. As always with graphs, choose the one you think best tells the story. I'm a stacked bar plot fan, but you might like group bar plots, and that's fine. The statistics that accompany these bar plots are displayed in a format that we call a contingency table. Why contingency table? Because we calculate perished and survived proportions contingent on cabin class. For example, the proportions of 0.4 and 0.6 for perished and survived in this table are calculated based only on or contingent on the total number of first-class passengers. The contingency table supports a quick exploration of the relationship among the two categorical variables and makes it easy to assess the size of that relationship. We know that there is a relationship if the survival rate differs for the different cabin classes. Indeed, it does. There is 60% survival for first class, 42% survival for second class, and 19% survival for third class. Cabin class makes a big difference. How do I know? I know because the proportions for survived are very different for each of the classes. I would consider this quite a large effect, especially considering the context is life or death. You may have noticed that if we add up the proportions within each cabin class that they add up to 100%. That's because they are contingent on cabin class. The fact that we calculated these proportions separately for each column is why we refer to these as column proportions. If we had listed these as percentages, we would have called them column percentages. Cabin class is the explanatory variable, so we needed to calculate proportions or percentages for each cabin class. We could have calculated row proportions, but that would not have been very informative. That would have told us the proportion in each class of those that survived. The rows would add up to 100%. There were different numbers of passengers for each cabin class, so this would not have been informative. We want to create our contingency table so that the proportions are contingent on the categories of the explanatory variable. Could we have created this table in a way that we would want to calculate row proportions or row percentages? Yes. All we do is flip around our table, as I have done here. Notice that the proportions in these two tables are the same, but in one table the categories of the explanatory variable are columns, and in the other table they are rows. What yields a relationship in both graphs and tables are changes in proportions for the different categories of the explanatory variable. Here is what a graph would look like if there was little or no relationship among the categorical variables. In this example, the variables are gender and whether the student passed the test. Notice that the pass rate, given here in blue, is about the same for males and females. That means that pass rate is not associated with gender. I purposefully chose pass rates that were slightly different because I did not want you to get the impression that the only time we will walk away from a statement about relationship is when proportions are exactly the same. The size of the association in this example is not 0, but it is very small, and certainly not worth writing home about. That's why I'm referring to little or no relationship. There is no relationship of any importance, so I'm not going to discuss a relationship among gender and pass rate. Also notice that no relationship does not mean that the pass rate equals the fail rate. We can have small or large pass rates and still have no relationship of gender and pass rate. The important point is that the pass rate must be consistent for males and females for there to be no relationship. The rate can be low for both, moderate for both, or high for both. In each of these cases, there is no relationship. In a contingency table, we would see the same or close to the same pass rate proportions or percentages for both males and females. Analyzing categorical variable relationships involves graphical illustration with stacked or grouped bar plots, calculation of proportions or percentages to display in a contingency table, and the study of the statistics in that table. In the next video, we will see how to create these graphs and calculate these statistics using R.